things off here. Um, Today we're going to be talking about estimating project savings, specifically for process cooling and refrigeration. My name is Amanda, and I'm an energy coach with Save On Energy. And I will be helping to sort of facilitate the early stages of this session and sort of help with the Q&A. We also have Todd and Sean joining us as our subject matter experts, and we're going to do more of an introduction to them as we get going. I just wanted to give a heads up that for this webinar workshop, we do have a participant workbook. So this is a Word document that we're going to drop in the chat for you, a link. You can download that, and you can use it to follow along and take notes. It's actually sectioned out sort of with the content as we go through. So a lot of the content that is in the deck is actually in the workbook, and it's a great resource for you to take away after with calculations and all kinds of juicy information in there. So please do utilize that. So why are we here today? So we will be talking about using a process-driven approach to estimate savings, which involves applying a four-step framework. So along this pathway, we will include specific and special considerations for process cooling and refrigeration projects. And really the best part of having our industry specialists here, our goal is that you will walk away with expert insights to confidently address questions and be able to refine your existing techniques for estimating savings for your various projects. So there's a lot of value to applying a structured approach to estimating savings for any project. The main benefit is that it will reduce your risk of errors that can lead to, disappointing results or even misapplied resources. So to reduce the risk of that happening, first, it's crucial to align your saving estimates with the required level of accuracy. So not all projects need the same level of detail. So you should tailor your analysis to really match the stakes. For smaller projects, a high level estimate might not be enough. Sorry, for larger projects, a high level estimate might not be enough. But for larger, more impactful initiatives, dive deeper into data to ensure accuracy. Avoid over or under analyzing and really aim to strike the right balance. For the second step, try to avoid making assumptions that don't apply to your specific system. So a common pitfall in these situations is borrowing assumptions from previous projects or industry standards without fully considering if they fit your unique scenario. So every system and project is different, so take time to understand the details of your project before applying assumptions. And lastly, make it easier to identify when saving estimates are unreasonable. To do this, establish clear benchmarks and thresholds for your estimates. Also, trust your gut. If something feels too optimistic or too conservative, take a second look. By following these steps, aligning accuracy levels, avoiding misleading assumptions, and scrutinizing unreasonable estimates, you'll significantly reduce the risk of saving estimation errors, ultimately leading to better project outcomes. So what does a structured approach look like? We've developed this basic four-step framework that can be applied to estimate energy savings in any project. So I will let Todd and Sean really illustrate what this looks like in practice, but at a high level, the first step is to determine if your data will meet your needs by matching it to your comfortable level of uncertainty. So I'll talk a bit more about that on the next slide, but an early assessment of your data will give you more confidence in your estimated savings later on. So the second step is to establish a baseline to understand total energy use and have better ability to identify errors. And the third step is to identify and understand the various savings mechanisms of your system. So it's important to think about how your system might react to changes to avoid incorrect assumptions or missed opportunities. And then finally, the final step is to estimate savings. So selecting the right calculations, the right rules of thumb based on what you've learned in those previous steps. So to talk a little bit more on that first step of assessing available data, part of that assessment might include a measure of your effort you need to put into your data versus the accuracy you need to require. To know what level of accuracy you require, think about what decision you're trying to make and the risks of getting it wrong associated with that decision. So an example might include the decision to make a big CapEx purchase. At a high level, the associated risk might be underperformance. So this chart is really purely for illustrative purposes. The curve would obviously be different for each unique situation. I think this curve can be even steeper for your typical project. If you make really the best use of data available to you, you can probably get greater than 60% accuracy for 20% effort. And that's kind of the point of today's workshop. To achieve that, all you need to do is make the best use of the data available to you. And a final note, always stop and take stock of what information is readily available or could provide a reasonable proxy before jumping into data collection or calculation. So that's enough spiel from us on the framework and why we think it's important. I'm going to turn it over briefly to Todd and Sean to talk a little bit about who they are, their experience in the world of energy management, and a bit about Elatico Consulting as well. Oop.
Well, good afternoon. It's nice to see some familiar names. I'm Todd Salerno. I'm the Conservation and Energy Lead at Elatico. And with respect to what we're doing today, I've spent probably about the last 8 years working with individual customers, helping them identify and quantify opportunities, doing baselines for them, which includes, calculations as well as submetering, helping them with their M&V and the ISO application process.
Thanks. Yes, I'm Sean Pittman, also with Elatico, coming up on almost 10 years here in the energy efficiency sector, working primarily in technical review, M&B activities, and also working directly with clients, conducting energy audits, system analysis, evaluating efficiency opportunities, M&V, and seeing projects through implementation. So looking forward to discussing some process cooling items with you today. Firstly, we'd just like to introduce a little bit more about Elatico Consulting ourselves. So we were founded in 2005. We're a privately owned, customer-centric energy services consulting firm, and we have two primary areas of focus. Firstly, conservation program design and delivery for system operators and utilities, and also energy and carbon management services to help businesses improve their environmental and economic performance. So included in those services, we have facility and system audits, M&V, energy management plans, carbon inventories and management strategies, and among others. So you can visit elatico.com to get some more information on those services or to get into contact with us.
Excellent. So before we pass it over for the rest of the presentation, I just wanted to say that, having these industry experts is, we're super lucky to have that. And I definitely would love for folks to ask questions. So please do feel free to use the Q&A. I'm going to be monitoring that. You can also use the regular chat, or just feel free to, raise your hand, turn on your camera and mute and ask questions directly. Yeah, that's kind of all I wanted to say, that we're going to leave probably about at least 20 minutes for questions at the end, but feel free to plug them in or ask them as we go along.
Yeah, thanks. Yeah, we're not a big group here, so if anybody wants to chime in whenever, I'm sure we can we'll have enough time for that for sure. So to start us off, we're just obviously here, we're talking about energy savings and process cooling systems. So process cooling systems obviously involves a lot more than just a chiller. It's a system that mechanically removes heat from a process, and that involves not only chillers, pumps, fans, motors, distribution systems, so the pipes and the valves and all the things that go along with that. These systems, if you're in a energy intensive industry, process cooling can be a really big piece of your end use on a facility level. We've seen them anywhere from 15 to 40% of the total facility energy consumption is consumed under those process cooling systems. So it's very important to understand how those systems work, and they often have some really good energy savings opportunities within them. So when we are assessing the available data, again, we want to take a systems approach and make sure that the data that we're collecting covers the full system and not only just the chiller. So we want to make sure we have information on our cooling tower, our water pumps, both condenser and whatever our chilled water circuit is, if you're using chilled water, um, and along those cooling loads as well. So anything, so here we have a description showing an AHU cooling coil that could be, multiple heat exchangers. It could be other pieces of process that require heat removal. So we want to make sure that we cover everything within this, and now we're not just concentrating specifically on the chiller. Todd, I think you had something else you wanted to mention on this one too.
Yeah, like each one of these is a subsystem of a larger system, and it's really important, like Sean said, is to really get the information on each one. Like for example, like you could have do you have a bypass loop to the cooling tower from the condenser pump? Changing one component of the system could possibly affect other components of the system. So that's why, if you're looking at maybe just a chiller replacement, well, you should look at all the components of the system in order to understand what the change might do to affect them.
Right. And to reinforce that fact here a little bit, so obviously energy savings often have trade-offs between how much energy is used in different components. So that's why we do take this system view. But to illustrate that here, this pie chart here shows the cooling energy end use by equipment type within the process cooling system. So again, chillers are the biggest piece of the pie, but they are actually typically outweighed by the combination of all of the other components that form this process cooling system. So while we do concentrate a lot on chillers, it's very important to incorporate these other pieces, because if you do something to the chiller that causes one of these other components to work harder, you do eat into whatever savings you achieved on that chiller. And there's always these knock-on effects that we need to understand. And so when you're collecting your data, you really need to keep that in mind. So what are we looking for specifically? In an ideal world where you have everything measured, measured kilowatt amps for key components is fantastic. Logged temperature and flow for both chilled water and cooling tower circuits, pressures across almost all system components, and logged production data. That would be ideal case. As most of us know who live in the energy world, you rarely do you get all of those things, if half or a quarter of them. But at a minimum, if you're looking to start investigating your system for establishing some energy estimates that are reliable, you really need at a minimum equipment details and specifications. So that's going to include for any constant or variable speed chillers or pumps. You want to know the compressor and pump ratings and efficiencies, chiller load profiles, you need the operating hours, the temperature set points, and logging of temperature and flowed chilled water circuits. With those pieces, you can start moving forward. If you're missing many of those, like if you're missing a couple, you can make it work. If you're missing a lot of them, it's going to be very difficult.
So
So
I
question
had
to
I was
yeah.
gonna add something on that too. Like there's a lot of small things too that you can pick up. Like for example, I've run into situations where you're looking at a system and then I notice that they've used isolation valves to throttle the flow of certain areas. Those things should also be noted. Equipment condition, how you could have pumps that are leaking seals or making a lot of noise that may also need to be replaced as part of the retrofit. Another one I've found very useful is going through the chiller logbook. Most of the larger chiller plants, and especially process refrigeration plants, have to have a logbook, and they can give you a lot of information on pressures and temperatures as well.
Yeah, it's a very good point. Yeah, noting valve positioning. Absolutely.
We have one question in the chat. I just wanted to pause for a second. I don't know if
Yeah,
we want to address it now or
sure.
maybe save it for the Q&A. It's around sort of factors specific to M&V of refrigeration systems, important to affecting the possibility of any sort of M&V, and what minimum would be needed to use assumed savings approach. So the Q, are these ideal and minimum available data for pre-project assessment or post-project? Oh, I think the question actually, the second question might have been on the content that you just presented. So do we want to revisit these or anything on
We
them
can
now?
we can stop and maybe chat about them. So maybe take the second question first. It's a little simpler. So these ideal and
Sure.
minimum available data for pre-project assessment or post-project. This would really be minimum available data for pre-project assessment. But I would say that whatever you're collecting in pre, you really should be collecting in post. Right? There's if you're identifying something that is a key component in your energy savings estimates, or it's influencing how much energy is being consumed by your process cooling equipment, then you're going to need it in post as well, because you're going to need to follow a similar process to determine how much the post retrofit equipment is consuming as well. So it is both, and in most cases you're going to need to have that data in both sides of it anyway.
Great.
So the second question, what are the factors specific to M&V of refrigeration systems important to affecting the possibility of any sort of M&V? What minimum should be needed to use assumed savings approach? It's difficult to answer that question because it's very system specific. Um,
This might be a simplified answer, but in reality is if you look at your monitoring period, you have to be able to really be able to repeat, or the monitoring period has to reflect what it'll look like annually. So if
right.
with regards to, your production levels have to be something that you can repeat over the course of the year. I don't know if this makes sense, but
Yeah.
uh,
Yeah, that reporting period, or so whatever period you select for your M&V boundary in pre and post, should be similar and should be reflective of full operating cycle of the system. So that's one key thing. The other is, this sounds like you're specific to categorization, that you're not meeting certain thresholds for either uncertainty or accuracy that are requiring you to report these projects as, M&V not possible or savings assumed. So it's difficult to say what are the specific factors to that, but in most cases, those factors are, or what I would assume those factors are probably, interval meter data of energy consumption, chilled water flows, chilled water return and supply temperatures. The key components to measuring how much energy is being consumed by the processes and their efficiency. So it's difficult to say what specifically there's. I hope that maybe answered some of them.
Yeah, and maybe when we have the Q&A section, if there's time, Max can ask specific questions. But it sounds like he's saying that helps. So let's
Okay,
keep
good.
moving. I think we have a
Great.
question for them now, don't we?
Yeah, give you a little bit of time to think about it. So what data do you have available for your process cooling equipment? So kind of curious, where do you house this data? Is it in a BAS system? Do you have a reliable set of data that for all of your chillers or your process cooling equipment, or is this all in a logbook, or do you have nothing? So just some examples there would be great.
Yeah, and maybe folks can put that in the chat as we keep moving, or if anyone wants
Yeah,
to share, we're open to that as well.
we'll keep moving. If anything pops up, we'll give it a read. Everything from to nothing. Yeah, that sounds appropriate to what we see. You do get that wide range, right? Sometimes you have everything, sometimes you have absolutely nothing. So,
Do you know, all the M&V work I've done over the last few years, I've never been totally satisfied with the information I get.
yeah,
There's always information you want that you can't get.
yeah, absolutely, absolutely. I would also say too, something to keep in mind when you do get, and it hasn't come up here, but I've seen it in many projects, is we'll get information and somebody will say, yeah, here's the kilowatt usage of the chiller, but we don't really know where that data came from. They don't know what meter read it. They don't know what it was based on. It may be based on an amperage with a formula built into a BAS system. It may have a three-phase energy meter on the chiller. Not really sure, right? So it's also good to not only know what information you have, but where is it coming from and what feeds into giving you that data, because there may be assumptions in the background where that data comes from. And I'll touch on that again here in a second. So how do we fill data gaps is a big piece, right? Obviously, like we said, we don't always have this information. So we use engineering calculations, and this one formula here will probably appear in any process cooling energy savings estimates that you do. It describes the heat energy flow within a boundary. You can set that boundary. It's usually through the condenser or a piece of or a cooling load. Where Q is the heat energy, M is the mass flow, Cp is the specific heat capacity of the substance, and delta T is just the temperature change between the 2 points. So with that information, you can determine how much energy is moving across a boundary. So you could set this across the condenser and see how much cooling energy or tons of refrigeration are being supplied by the chiller, and you compare that to the electrical energy of the consumption of the chiller, and you can find the COP. So that falls under additional information. Using operating hours and average COP are great ways to fill in data gaps. If you're using average COP, you can base that on the chiller performance curve and the cooling load. So finding Q, finding the chiller performance load, and then you could potentially get a rough estimate of input kilowatts if you don't have that. It's important here to note that incorrect estimates of flow are one of the largest sources of error when estimating energy consumption. So flow obviously forms part of this Q equals MCP delta T equation. This equation is often used in determining energy consumption or efficiency of the chiller, and it flows into nearly all of the calculations that you'll do for when you're estimating savings. Specific heat capacity, you can look them up in thermodynamic tables. Delta T is usually read just either straight from a BAS or it's a very simple temperature gauge. Everybody has that information, but the mass flow rate is one that not everybody has. Not everybody has a flow meter installed to read those mass flow rates. So if you're using, say, a specification to estimate the mass flow rate, and that specification is based on what it was supposed to be commissioned at 15 years ago, not what it's running on right now, that introduces a large source of uncertainty in your savings estimations that flows through almost every single step of the estimation process. So having a high degree of certainty on your flow rates really helps reduce the total uncertainty of whatever savings estimates you're doing.
Sean, I have a quick question on the gaps, and if you're going to answer it, please stop me and keep going. But I'm wondering, you mentioned data logs. I think there was mention of the data log books and logging data. If people don't have data and they're looking to start logging data, do you have any areas that you would prioritize that they start with, like for big wins or for kind of getting some good juicy data? I guess it depends on their project, but just curious over that.
Yeah, it does definitely depend on your project and what you're doing, like specifically, but usually, obviously, with chillers being the largest piece, understanding how much energy that chiller is consuming is probably the biggest piece of information you can get. And then second to them is chilled watt for flow rate or um, temperatures, trending temperatures between chilled water supply and return over time. So that you can estimate the efficiency of those chillers and understand what that chilled water flow rate or chilled water loop is doing.
I guess there was another question there too about ultrasonic metering, and which was a good question.
Yeah, this is a good one, and I think it's probably applicable to answer it now. Um, the question is CHW flow rate is rarely measured. Is it common practice to do ultrasonic clamp on meter measurements if possible?
Yes, yes. If you can do a clamp on meter to measure the flow rate, by proxy, that's definitely um, seen that applied lots of places. Yes,
Okay. And what
and that
what about the accuracy of that, I guess? Sorry.
yeah, anytime you're using a meter, you have to incorporate the accuracy of that meter within your calculations, and so you need to follow through to calculating your project savings uncertainty to understand whether that amount of uncertainty is acceptable for the outcome you're looking for. So, yeah, go ahead, Todd.
Yeah, from my experience, I've used the clamp-ons, the ultrasonic meters. I don't know, maybe I'm too old school, but I find I have more confidence in reliable pressure gauges on the suction and discharge, as well as balancing valve settings and things like that, that I've found that I've had relatively good confidence in what the flow is. And you can kind of double check that when you have the delta T taken into account and the power readings of the chiller. Then you can kind of say, yeah, the COP is in the ballpark. But if you could get ideally, if you had a reliable ultrasonic meter, that would be great. But for the most part, I've been satisfied with the flow readings by doing the other method.
Fair enough.
Sorry, Todd.
Go ahead, Max.
Sorry, I just wanted Todd. Could you just explain that again? The alternative to the clamp-on, because I'm very interested in that.
What you do is if you have reliable pressure gauges on the supply and inlet of the pump, and you can determine, through the pump curve, what if you actually also take a power measurement of the motor to verify, you can get a pretty good idea of what the actual flow is. And
Okay.
then if you have like Flowtrex valves or equivalent on there, and you know what the settings are, that can help you as well.
Okay. Okay. Cool. Thank you very much.
Yeah, that's good. That actually kind of leads a lot into our next section here, is what to do about that missing data. So obviously, real world data is challenging, as we all know, and we're discussing. So installing more data logging is obviously a great way to fill in those gaps, not always feasible or time allowable. But using proxy data, really just what Todd just explained there, right? Using the data that you have on hand to find something else that you don't have. So you can use those pressures and those pump curves and the power of the pump. If you have all that information, then by proxy, you can find the flow rate. And then you can use that flow rate with the COP and the measured energy of the chiller and the Q equals MCP delta T to try to verify, is that the same flow rate that I'm getting through my chiller. So you're not directly measuring that, but in multiple ways, you can find it by proxy. And if you're doing it by proxy and you can do it by multiple ways, then you feel much more comfortable in using it because you've verified it in more than one method. We can also do modeling and estimating. So anybody who's been involved in the savings world will understand that we obviously don't have that big picture, so we usually use some sort of modeling or regression or linear regression. Obviously, I think most people will be pretty familiar with that approach. So taking a smaller group, finding a relationship, using that relationship to expand to a larger data set. Obviously, just use your logic and best practices to apply that as you will. So some common errors, or what most people get wrong when they are using data or collecting data in this first step. So using spot measurements instead of trends. So as will be a recurring theme here is that managing, or when you're developing baselines or doing estimates, you really want to try to capture the full operating cycle of a piece of equipment, especially with chillers, especially with pieces of equipment that are influenced by outdoor air temperature or production rates. If you use a spot measurement at peak, is that going to hold at a lower production estimate? If you measure it in the summer, is that the same as measuring it in the winter? So not having a big enough sample really can affect the accuracy of your savings estimates. Similarly, assuming cooling demands are constant, they may be very production driven, but they may not be constant all the time. Are you going to have a change in your production line that's going to affect what those cooling demands are? You can use whole building utility metering to estimate your process cooling load if that load is a significant portion of your total utility meter, but only if it is significant. So I think IPMVP is 20%, and even then, it's not that discernible. But sometimes we've seen people try to, a 10%, and they'll say that that's a significant enough to see the variation, but it's tough. So not appropriately considering production and manufacturing levels, or again, using too small a data set or one that doesn't span a full operating cycle. So outcome of step one is your outcome of having an accurate data assessment. So you will have a reliable and defensible data set, and that'll form the foundation of data that is going to be your accuracy requirements. Once you know that you've met your accuracy requirements, you will have an understanding and of the uncertainty and the data gaps that are within your data set. So that will lead you to knowing, well, if I move forward with this is the amount of uncertainty I probably have within my data. Is that acceptable for the project or the evaluation that I need to perform on this project? And by understanding what data is available, you can have confidence that your energy savings calculations will reflect the reality of your systems. So the second step in the framework is establishing an accurate baseline of energy consumption. So this is an estimate or measure of the total energy consumption of your system, typically over an annual period. Understanding energy consumption over different seasons, production schedules, and types of operation, and we'll consider the runtime, duty cycle, and partial loads. So we've broken it down here into kind of three separate categories: methods of estimation for your baseline. Firstly, we have a basic approach, which is really kind of back of the napkin, go, no go, like really quick, power times time, maybe nameplate information only, how much energy it's using. If we could save 50%, is that enough money for us to make any investment into looking into this? Second would be more formula-based approach, using specifications, load profiles, temperatures, and process load data to develop an Excel-based baseline model, typically done hourly with some sort of COP calculation repeated for every hour that would give you either energy or efficiency and calculate out energy consumption for you. And lastly, the more advanced approach would be a modeled approach, typically Excel-based linear regression, sometimes multivariable, or software-based model. Those would typically be third-party, might be something of a black box at your end, usually built in Excel on the back end anyway. But those are really for big, complex systems, multiple chillers, multiple process loads, all intertwined, would you get to something requiring a software-based approach. So question again for the group: what approach do you typically use in your daily analyses? So someone to ask you how much energy is being used by your process cooling system, what approach would you use? Would you use a very basic approach and say, I know on average it draws this many kilowatts, we run 12 hours a day, 12 hours times our kilowatts times the year, that's how much energy it uses? Or do you have an Excel model kind of built already that takes in more information than that? Both approaches are acceptable, really, depending on what your needs are. Okay, we'll move on and see if any of those trickle in. Well, we got one basic using power use. I think that would be my expectation for most daily kind of use. If you weren't specifically looking at a project yet, that would be kind of where I would think most people would go. So again, very basic. Kilowatts is volts times amps times power factor times square root of 3. Using that kilowatt, we can multiply by the hours of operation and get our energy. And just definition of COP as useful cooling energy over power input. So Todd actually is going to take us through just a quick example of calculating a baseline.
Sorry,
you're
I
on
was
mute.
muted. Yeah. So basically what you would do is the whole point is to calculate cooling load under different operating conditions. So in this example, the chilled water flow rate varies between, 0.05 and 0.1 meter cubes per second. Of course, don't ask me what that is. I'm an imperial guy. The inlet temperature varies between 10 and 12 degrees Celsius, and the outlet temperatures vary between 6 and 7 in this example. So it's a pretty tight, um, uh, consistent amount of flow and temperature there. So if you go to the next slide, you can see from that graph that was on the previous slide is they had a graph of if you look at this column right here, the far left column, the percent load, the hours per year in which that level of cooling load occurred. And the second column, Q, is the amount of kilowatt load that is calculated from that. And from there, you would have what is the COP at that specific load. And from there, you can calculate what the input kilowatts are for that cooling at that load, multiplied by the number of hours per year, and then you get the megawatt hours per year. So, I mean, this is all easy in a chart. The hardest part is determining, this is, to me, the most important part of it. You can always figure out what your COP is because there's lots of published data on the different cooling equipment and what the input kilowatts are. The important part is determining the load hours per year. It's the hardest part, but it's the most important part because if you don't have an accurate assessment of what your annual cooling load hours are, you're going to be way off, potentially way off. You might get lucky and guess it correctly, but this is the most accurate way to determine what your baseline energy usage is for that particular cooling system.
Right. Yeah, that's very true. Oh, sorry, go ahead, Evan.
No, I just wanted to interject because I think we had some related questions that came up a little bit earlier around calculating ideal COP versus average COP, and I'm not sure if in some of this you're answering that, but also Talha had a question around how to calculate useful cooling kilowatts. Not sure if it was cooling kilowatt hours, maybe. There was, yeah, maybe. Talha, if you want to unmute and clarify.
Maybe perhaps under here, useful cooling under our efficiency COP section here.
Yeah, yeah.
So that is there's a couple of ways to find that. If you had, like Todd was saying, if you knew what the input power was, and you had the performance curve of the chiller, you'd be able to determine what the COP is at that input power, and then you could rearrange this formula here to determine the useful cooling. You could also use that Q equals MC P delta T equation across the evaporator to determine how much useful cooling is going into your chilled water loop. Correct there, Todd?
Yeah. There is published data for most, I know for especially for centrifugal chiller systems and newer systems, there's the integrated part load value, or is it IPLV, where you can get what the CO or kilowatts per ton or COP is at the different loads. Now, when you're doing a baseline, you might have to resort to published data, but the actual chiller system that's in place, and it might have been there for 15 or 20 years, might not be performing at that level. But the one advantage to doing it that way is you are doing a fairly conservative estimate. So you know that the existing system will not be an efficiency higher than what those published values are, most likely. It'll be somewhat less. So you're conservative in your savings estimates. That way you don't make an error on the high side.
Correct. Yeah. Wherever we're making assumptions, always best to err on the side of conservativeness. Is usually a safe bet. There's another one in there. How do you propose estimating the hours at each cooling load? That's a great question because it's definitely something like Todd said. It can often be the most difficult thing to find. There's different ways of going about it. It depends on how much accuracy you need and how the system operates. I would say on the very simple end, if you have a measured period, you could apply that as a ratio across the year. So if you measure for a month, you develop this a similar graph like this that only covers a month of time, and you apply those percentages to 8760, and that's how you just extrapolated out that 1 month to a year. If you think your load is fairly consistent month to month, that might not be a bad approach. On the higher side or the more advanced side, maybe you have to try to find some variables that are influencing the load on that chiller, whether that's production, outdoor air temperature, something like that. And that goes back to our kind of model approach here, where we're going to start using formula-based approach to develop more formulas. Again, data filling, mitigation strategies to fill in those spots we don't have.
Yeah, like one example, like I guess there's different types, right? There's, for example, like a condominium or an institutional building, you're going to know for the most part your cooling load is most likely going to be related to weather. So that's how you can project the hours per year. And then you get onto the industrial side, you could be in a situation where it's a process that is fairly constant, or it varies according to units of production that you can relate it to. So that if you do your metering and monitoring and you get the energy data and all the other specifics, as well as the production data, you can do a regression that will give you a relationship between the production and the cooling load or level of cooling load. And then if you have the yearly production data, then you can do it, project it over the course of a year. Then if you get into some situations, especially like I found with commercial refrigeration, like cold storage and food processing, that can be a little more difficult because you're starting to get into batch processing. So you might have to get it narrowed down to what a particular batch uses and then project that over the course of a year.
Yeah, it's definitely one of those things you can get down the rabbit hole on pretty quickly on trying to find those multiple different approaches for different production processes. Okay, so again, we're going back to this, developing a model for more accuracy. So if you do need that higher accuracy, you can use the model-based approach. So obviously it's usually Excel, combination of bin analyses, regression formulas, hourly temperature, weather data. This is more in line for budgetary estimates, incentives, pre-designed project evaluations, where you'd want to get to this level of accuracy. On the right here, we just see this would be kind of the end result of using a model-based approach where you've developed relationships between the power demand and percent of rated load for a chiller plant at two separate entering condenser water temperatures. I think we'll let Todd here go through one of our real world examples from a mushroom farm. I'm mute again there, Todd.
Mute, yeah. Okay. This was a sample of a project where it was a mushroom farm, and they had two centrifugal chillers as well as two air-cooled scroll type air or cooling unit chiller units, and we had a real conundrum because it was a very large system, so a large part of their energy usage was cooling. So what we were able to do is, again, we metered the equipment took all the specific data down so we would know what the cooling load was with respect to outside air temperature, because we found when we were doing the metering that the biggest component of what the change in chiller plant load was the outside air temperature. And that was specific to the type of process that it was, where they were they were actually doing batches in their production, but the way they cycled their batches, it turned out that the load was fairly consistent. So the actual mechanical cooling load on the equipment was the same, but what caused it to change the most was outside air temperature. So we were able to develop a model comparing the outside air temperature to what the refrigeration load was, or the cooling load was in the plant, in tons. And that's the graph on the left. And then what we used is we used published performance data of all the equipment involved, the air-cooled units, the existing 2 chillers, and then the proposed new chiller. Now, to me, that wasn't ideal, but again, what I said is, at least when we do the initial estimate, we will err on the side of caution and be more conservative in our savings estimate. And you'll see at the end what happens is, you make that up is when you do your post-retrofit M&V, you catch those savings. So we use these two graphs or sets of data in order to create an annual model where we predicted what the consumption was of the existing chiller systems and what the new proposed chiller would do.
Excellent. So yeah, this is I think similar, just stepping through the process you just described there, right?
Yeah, like the annual data set of hourly outdoor air temperature. So we use the hourly temperature data to calculate what the hourly chiller plant load would be. And then we use the actual performance data of the existing units, as well as the proposed unit, to calculate the difference in what the loads would be.
Great. So again, some common errors we see within baselining. So not accounting for seasonal variability, I think, is a big one there. So if you're going to not account for weather within your regression formulas, I think you need to be very confident about that, and you need to show that you need to have checked at least, right? Don't just discount it because you think you're really production driven. That's something we see is a very common issue, and later on you can see that, oh well, we did use much more energy in post because it was much hotter that year. Overlooking system interactions are very similar. Ensure you plan ahead, ensure trending and logging of all baseline variables continues through to implementation and post-retrofit. So if you identify something that is impacting energy consumption during the baseline period, make sure that you plan to measure it in the post. Seems like a simple thing, but is something that's very common that we see that gets left out. And lastly, correlation does not mean causation. So we could have an entire webinar series on statistics and what R squared means, and T stat and P stat and all of that. But just suffice to say that a high R squared does not always mean that the correlation is relevant. And there are ways to make Excel go to the nth degree of multivariable regression that shows a high R squared. And that does not always mean that that is a reliable formula to use. So you do need to use some logic when you're applying these. If your performance curve is a big squiggly line because you've gone to the 8th multivariable, does that really make sense in how you think that chiller performs? So just keep that in mind as you do perform those analyses. So by establishing a baseline, you get an understanding of the total energy consumption of the system across all modes of operation. And this uncovers errors in our savings estimates because they'll become obvious when it's seen as unreasonable percentage of the total consumption. So it's providing those guardrails to keep savings estimates on track. So if you go straight to your savings estimate, you say, this is how many megawatt hours I'm going to save, but you don't have an understanding of what the baseline is, you don't really know what percentage of your baseline are you looking at. Are you estimating a 90% savings? Are you estimating a 5% savings? Are those reasonable? So having a good baseline gives you those guardrails, gives you a frame of reference to work within. So thirdly, understanding the savings mechanisms. So we want to understand how changes to the system affect how equipment works and how those changes can lead to energy savings. When we understand how the equipment operates, we can avoid over and underestimations, and we can verify that the estimated savings reflect reality. So this is a quick pie chart just to reiterate that savings and systems view from a recent chiller project that incorporated a new chiller control system. After implementation, this is by end use total savings. This was quite a large savings project, but we actually found that 40% of our total savings came from the condenser pumps by installing variable speed drives, and only 28% from the chillers. So while it was a chiller driven project and we concentrated a lot on those chillers, only 28% of our total energy savings came from there. The rest of it came from all the other system components. So jumping into chiller savings, which does affect all those other components because everything's connected, some basic chiller saving mechanisms. So we have reduced cooling load, we can reduce the chiller lift, we can improve efficiency of cooling, and we can reduce flows or pressures. So reducing the cooling load, we can install pipe insulation, remove unnecessary piping, disconnecting old loads, reducing the distance that chilled water has to flow and where it can gain heat along the way. Reduce heat sources in cooled areas can be really big and seem obvious, but is often an opportunity. And we'll remove scaling within that piping so that those flow rates are more efficient, or the pumping is more efficient. The impacts of these is that your chiller can run at a lower load percent, and just keeping attention to the part load efficiency of all our chillers is important. So this small graph here just kind of illustrates that as you move from right to left and you reduce the percent load on your chiller, obviously majority of chillers to a certain point will perform better at a higher efficiency and therefore save you energy. This here, so if we increase chilled water supply temperature, so this graph is showing on the orange line, the system energy consumption. The blue line is the chiller energy consumption, and the green line are the pumps. So if we increase the chilled water supply temperature, the amount of energy consumed by the chiller goes down, but the pumps have to work harder because under this assumption here that we have a constant load that needs to be served. So by the Q equals MCP delta T, if you adjust the delta T, but your Q needs to remain, something else has to go up. So that means your flow rate has to go up, which means your pumps work harder. And so you consume more energy at the pumps. So what we try to do is find that optimum point in the curve where we have the lowest amount of chiller and pump energy consumed. On the other side,
can you go back to that one for a second too? Like as well, if you change too much the temperature, the chilled water supply temperature, and you start getting a low delta T on the chiller, that in effect is going to reduce its efficiency.
Yeah, good point. On the other side, we can decrease condensing water temperature. Similarly, as we move from right to left now, the chiller temperature or chiller energy consumption will go down as temperature goes down, but the cooling tower must work harder to maintain that same Q. So again, it's a trade-off. Again, we're trying to find that lowest part of the curve here, and understand that there are impacts to different components when we change these temperatures. We can also improve the efficiency of the cooling itself, so of this specific chiller. So these are some of the common ones. You can upgrade to a higher efficiency unit. So just a straight one-for-one replacement. There's some really high efficiency units that are out now that will just perform at a better efficiency rating. We can also upgrade those to variable speed chillers to improve part load efficiency. So that's kind of shown on this graph here. The constant load chiller compared to a VFD chiller, and how their efficiency changes at different load percentages, and we can see the VFD far outperforms the constant loads chiller, as you would expect. Well, we can improve the sequencing of multiple chillers, so that would mean operating chillers at their ideal set points or where they operate at the lowest or their best efficiency, and sequencing when those chillers turn on when you have multiple chillers. Do you have a point there, Todd?
Yeah, it's an important slide because it also shows the importance of baselining, because if you baseline and look at the hours at certain loads throughout the year, you may find that your existing chiller is oversized. Usually I don't think I've really ever come across undersized chiller systems, and no one gets in trouble for oversizing, and you don't really notice it until actually just from an energy point of view. But doing the baseline helps you understand, if you are looking at replacing the chiller, how to do the sizing. You may find that you could go to two smaller units rather than one larger variable speed unit. That might be an option as well. So that's why it's really important to do the baseline to figure out how many hours per year you are at that maximum tonnage.
Right.
I think Sean froze.
I was wondering if it was just me or if it was
Yeah.
you.
Yeah.
Todd, are you able to oh, he's frozen, so he can't move the presentation probably.
Yeah.
So let me just quickly take over the sharing and hold on one second here while I get us to the where we're at. And are you able to speak to this or let's
We
just
went
make
through this
sure.
one. Yeah, we really got to. There we
Yeah.
go.
He's gonna join back in, I think, but let me just get you a screen here to look at so you can know where we're at. Yeah, so we wrapped up here. Is that right, Todd?
Yeah. Yes.
Great. And are you able to talk about reduced flow, or should we wait for
No, we can
Sean to come back?
we
Okay.
can we can talk about it and with Sean.
Great.
Really, all chiller systems have, when they design them, for a minimum flow and a design flow. And if you end up with a system where you're seeing that your delta T across your condenser or your evaporator is very low, you may want to it might present an opportunity to slow down the pumps or put the pumps on a variable speed. Then you're going to save pumping energy, as well as you're going to put the chiller delta T's at a range what they're designed for, and the chiller itself will work at a more efficient level. So that's really what the reduced flow opportunity presents, is that if you're, and you run into that situation when you have an oversized chiller, it happens a lot. And they're pumping water through at a certain flow, and you've got a very low delta T. So it gives you an opportunity to slow the amount of flow down and save energy as well.
Todd, are there any risks with reducing too far?
Well, yeah, because you also, you have your chiller, which is designed for a certain flow, and then you have your system. You have to make sure that you're pushing enough water through your system to do what it needs to do to provide the cooling to the end use. So yeah, there is potential risk with that. It's not necessarily cut and dried. You have to look at the whole system.
Great.
Thanks for covering there, Todd. Can
Oh, you're back.
blame Rogers for that one.
Yeah, I'm on Rogers too.
Yeah.
Sean, I don't know if there's anything else you wanted to add here. We're just talking about the risk of cutting back too far. But I think Todd covered it, so we can maybe move to the next one.
Yeah, sure, Todd. Todd did a great job.
Great.
Yeah, can move to the next one. So common errors about savings mechanisms, common errors and assumptions. So assuming linear savings. So it is not always true that your energy savings are going to scale directly with changes in load or temperature. So you need to consider system inefficiencies or part load performance. So those lines are not always a straight line. And that is something that we see a lot, and people making that assumption that just because at this load, it's going to save this much energy, that's not necessarily a straight line. Not adequately considering the role of control strategies. So something there is, the best control strategies in the world don't work if you don't implement them, right? So you need to make sure that if you're going to have a project that is based largely on the control strategy, that you have the proper planning and people in place to implement that control strategy. That's something we see all the time, that control strategies, the best thought out ones, if they're not implemented and they're not managed and maintained, then those savings just aren't achieved. And lastly, not considering future production or manufacturing rates. So undersizing or oversizing, similar to what Todd mentioned before about oversizing systems. You want to make sure that you have a long-term view of these, but that you're not oversizing, and then also that you're not undersizing. Otherwise, you will have poor system performance. So the outcomes of understanding the savings mechanisms, the biggest and the one that we all want is that the expected savings outcomes are achieved. So the energy savings analysis will capture all relevant data and system interactions, and control strategies can be planned and implemented. So again, if you've identified these things and understand how they work, then you'll be better able to implement those control strategies. So understanding the savings mechanisms within your system and your assumptions concerning those mechanisms ensures the savings estimated will reflect reality. So moving on to really the estimating savings portion here, the last step. There's some common rules of thumb that you can use for your high level analysis and just your initial investigations. Each degree Celsius reduction in entering condensing water temperature typically results in a 1 to 2% increase in chiller efficiency. Each degree Celsius increase in chilled water supply temperature will result in a 1 to 2% increase in chiller efficiency. So these are broad generalizations, but they do tend to hold across the majority of chiller plants. Older chillers, just the chiller itself, can consume up to 0.6 kilowatt per ton of cooling. That's pretty easy to hit that high mark. And variable speed drives on chillers can result in up to 30% of energy savings. So just some broad pieces to kind of guide you in your energy savings estimates. This is a great little chart here that you can use to reference how your chiller plant is performing. So this is all components of your chiller or your process cooling system, not just the chiller. If you are performing at less than 0.7 kilowatts per ton for your plant, that would be considered excellent. We see that for maybe all variable speed chiller plants or high efficiency optimized chiller plants. Whereas if you're performing at greater than 1 kilowatt per ton or 3.5 COP, then we would say that you are in a needs improvement or the opportunity for improvement within your system. So there are probably correctable design or operational problems within that system, and there'd be pretty good opportunity for some significant savings. So yes, I think Todd's gonna talk us through here is upgrading to a variable speed chiller.
Yeah, this is just a quick and simple explanation of how we went about estimating the savings of converting from a constant speed centrifugal chiller to a variable speed centrifugal chiller. Again, if you look at the table to the right, we established what the load, the baseline was measured that way, is we established the load over the different hours of the year. So we had estimated the hours for each percentage load. And then we were able to calculate using the graph on the left what the existing chiller kilowatts per ton of refrigeration would be based on published data for the chiller. So anyways, it was probably much higher than that, but since we used published data, assuming it was a brand new chiller, we erred on the side of caution. And then what we did is we used the published data for the retrofit chiller, kilowatt per ton. And then we calculated the hours times the kilowatts per ton for the existing chiller and the retrofit chiller, and then we determined the savings. Now, the nice thing about this is there's uncertainty based on using published data, because one, there an existing chiller, which the performance is probably not as good because it was like 20 years old. And then the new chiller, we assumed that it would perform according to what the published data was, but that is all picked up in your post retrofit M&V. And using that methodology, we found the savings were much higher than what we originally projected from the post retrofit M&V. But I would say the most important part of that table is nailing down what the load is over the course of the year. Everything else can be adjusted, according to looking at published data or going in and actually doing measurements of the existing chiller if you're not confident enough of it.
Yeah, Todd, I think that's a great point. I think this, it just really illustrates the importance of the baseline and that load, like you mentioned. And if that's not accurate, the savings are really not going to be correct, right? So I love this example, this illustration here. Thank you. Great. Sean, did you want to kind of wrap things up here before we get into the Q&A?
Yeah. So yeah, just some final closing remarks here. So, by employing the systematic approach, you can be confident that your saving estimates are grounded in reality. So the final output is you get a defensible and repeatable analysis that you can use to prove project savings to evaluators and internal stakeholders. And you can avoid inaccurate estimates that put your reputation at risk and question the value of energy efficiency initiatives. So a final reminder, ongoing data logging, measurement, and verification activities will ensure that energy savings persist in the future. Again, something that we see very, very often is that you don't have that follow-up and that ongoing M&V activities to monitor and observe the changes over time. So you may have ongoing logging and data metering, but is anybody looking at those? Are you verifying? Are you identifying quickly when things deviate or drift from the project outcomes or objectives? Sorry. So yeah, that's very important to always keep that ongoing process of monitoring and measuring and re-verifying to make sure that those savings persist over the long term.
Thank you, Sean. I almost forgot I was muted. Thanks so much for that wrap up. I think we do have a little, maybe 15 minutes or so before we kind of wrap up for any questions that may have not been answered sort of during that session. So I'm stopped sharing here just so if anyone does want to use their camera, we can see you clearly. But let me just check the Q&A here. Yeah, I think most of the questions have been sort of asked in the chat, but I would love to open it up for anyone to unmute and share their burning questions that may have come up during this last section of the presentation.
How to calculate the heat recovery chiller savings?
So that's how do you calculate heat recovery chiller savings?
Yes.
You would probably need to have a measurement of how much heat energy is being recovered through the heat recovery system.
Is he referring to recovering heat from the condenser loop?
Yes, recovering the heat from the condensing loop. And yeah, I know that, yeah, we can calculate if it is fully delivering the heat to the domestic hot water, we can say that complete domestic hot water energy is saved.
Mhm.
Other than that, if we are adding to some humidification or something else.
Yeah, so you really your limiting factor will be how much of the, like, for example, if it's your preheating domestic hot water, you know it's coming in usually at averages, I think, about 60 degrees or 55
Mhm.
degrees from the city or town.
Mhm.
So you have to look at you know, at what condenser temperature can you get useful heat out of, right? Because you do have approach temperatures with regards to the heat exchanger. It might be like, you know, you can probably start using the condenser water when it reaches 60 degrees and above, and then, you know, then you have to calculate how much heat you can recover and what is the pumping energy required in order to reclaim that heat, right? Because you're going to have to pump probably
Mhm.
condenser water or use a valve. Well, you could potentially use a valve, but most likely you would have to use a pump to pump it through the plate and frame heat exchanger.
Understood. Thank you. One more question regarding the cooling towers. So if the water is so hot and the cooling tower is getting scaled up, what are the suggestions or other energy improvement methodologies to be followed for those cooling towers?
Um, for the most part, scaling, like, it depends on the type of cooling tower too, right? If it's an induced draft cooling tower, really you're getting atomization of the water as it falls down through, and then the air flows in 180 degrees in the other direction. But I think with uh, the metal type blowing cooling towers, your scaling could affect the nozzles and increase your pumping energy. So most condenser water systems they usually treat the water with either an algicide and an anti-scaling compound as well to keep that at a minimum. But it will affect the nozzles if they scale up or scales up too much and increase your pumping energy.
Thank you.
Thanks for those questions. Any other questions from our participants?
One more question from my side is so what kind of so for this cooling chilled water loops, so are there any available solutions or the chemicals which can improve the heat transfer?
On the chilled water side, they have anti-scaling chemicals, as well as sometimes they treat the makeup water that goes in. But you don't get as much scale development. Maybe you have more info, Sean, but when you're at 42 to 60 degrees, you're not going to get a lot of scale buildup. Most of the scale buildup will be in the actual evaporator and condenser tube bundles. But that's why you have usually have a water treatment program for your chilled water.
Yeah, I have heard of some additives that you can add into your water that will improve that are supposed to improve heat transfer just on their own by just being an additive to the water. I don't have any direct experience with it. Maybe something I can provide afterwards, a link to the product. Again, I've only been advertised to me. I've never seen it in work, but I know they have quite a few white papers of instituting it more in heating processes than cooling, but I believe it would work just the same in the cooling side. So maybe that's something we could provide after. The name of it is escaping me, but not something I have direct experience with. And
Endotherm,
so I'd
right?
be
I think it is
there. Yeah,
endotherm.
endotherm. Yes,
Yeah.
exactly. Yeah, that's the one.
Yeah, but mostly it is used for heating loops, right? Hot water
Right.
loops. Yeah.
Yeah, I don't know of
Uh,
anything specifically geared to cooling loops.
yeah, I think cooling, I think most of the systems doesn't need the additives maybe. Yeah.
Yeah, it might be at the delta T might be low enough.
I think we have a question from Al as well, so I'd like to give Al an opportunity to ask that.
Sure, thank you. And this is maybe a basic question, but when you talk in the example about a variable speed chiller, are you talking about the chiller itself, so the variable speed on the motor, on the compressor, or are you talking about variable speed pumps circulating water?
Oh, the compressor drive
Yeah, okay.
is variable speed.
And is it possible, I've dealt with compressors that are fixed speed, or chillers that are fixed speed. Is it possible to change out the drive on a compressor, or are you better off to buy a whole new chiller as part of the package?
There's two complications. Is a lot of the chillers, the motor is encased to and surrounded by refrigerant in order to provide some sort of cooling effect to the motor, as well as when you have a fixed speed chiller, it's basically designed to run at a fixed speed. They'll have for bypass, they'll have like inlet vanes and things like that. So you'll be very limited in your amount of modulation that you can do with the drive. I've never run across a variable speed retrofit where they've retrofitted a fixed speed centrifugal unit to a variable. I've heard of it, but I have not seen one.
Okay, thank you. That's more or less what I thought, but I wouldn't want to tackle it myself. Thank you.
Any other questions? We have a little bit of time. I have some that I can definitely add, but I would love to hear from our audience if we have any. Well, I feel like one thing that really stood out to me is the importance of baselines. And I was wondering for a system, when folks are calculating the annual baseline, or the annual energy consumption, what are common sort of pitfalls or challenges or mistakes that happen when they're calculating that and estimating the annual energy consumption? My mouth isn't working anymore for speaking. Yeah, common things people do wrong. I think that's something to consider because I think we all have been there before.
I'm an
Yeah.
expert on that.
Yeah, doing it wrong. I think something common is just people, going back to just using too small of a data set or too small of a sample size and assuming that can be representative of the full year. And that's not something that people do, as a mistake. It's just a consequence of time and money and resources that sometimes you have to work with what you have. And so I think the point of just trying to be as conservative as you can in your estimates, especially when you know you're working with a smaller sample set than you probably ideally like to have, is really important to keep in mind, because we are often forced to move forward with limited data or half the picture, and so you have to make sure that you keep that in mind as you move through your estimations.
Yeah, I would say that, and only focusing on the equipment to be retrofitted and not looking at the whole system. I would say that would be probably another pitfall.
Right. So just concentrating on that chiller replacement, but not considering the impacts to the cooling tower or your condenser pumps or something like that. Yeah.
Yeah, all the components that you were kind of talking about early on that fit as part of that sort of taking a systems view of things. Yeah. Great. Excellent. I guess, doesn't look like we're having too many more questions. Any final kind of thoughts from Todd or Sean before we sort of wrap this up?
You want me to go first? Oh, well, thank you for the time. And I think if anything, is really nail down the baseline.
Mm.
Then everything else could be fixed. But I've run into situations where I'm doing the post retrofit M&V, and I wish I did this on the baseline and get it more accurate.
Yeah. It's worth the extra time and effort, sounds
Yes.
like. Yeah. Great.
Yeah, definitely. I mean, just kind of echo that again. It's more data that you have in the beginning, the better. You can always you can never go back and get data that you missed out on getting the first time. So get as much as you can. Data's cheap these days. If you have the meters, record it. If you're not logging, start logging now, because you never know when you're going to need it. And storing a CSV file of some information really doesn't take much space or cost these days. I think we may have had a question there, actually.
Yeah, let's hear that, because we do have a bit of time. Talha, did you want to unmute? And I'm so sorry if I'm pronouncing that wrong as well. I think.
Hi.
Oh, there you go. Hi. Hello.
How much HVAC required if I know any building? I am from Pakistan, but I know I am in living in this building. There is no HVAC. How to calculate the HVAC is required in this building?
So how do you calculate your heating and cooling loads for a building?
Exactly.
Yeah, so there's some references you could use. I think ASHRAE has some standards based on cooling load for different components. It depends on what's in the building and the construction of the building. That is could be a whole webinar on how to calculate heating loads for facilities. I would say your best bet might be, if you're looking for a resource that maybe has some guidelines or rules of thumb, maybe ASHRAE would probably be a good place to start, or building codes. I know the Ontario Building Code has some information as well. I don't know, Todd, if you have any other resources that might be useful off the top of your head for that.
Like you said, the ASHRAE values has kind of estimate ranges, but if you have a building and you say you want to parse out your heating and cooling load, and you don't necessarily have the metering data or metering equipment or anything or time to do it, it would be to inventory all your non-heating and cooling loads, get their operating hours, and assume that is what your base load is for electricity. And then from there, you can look at your annual usage and see the change according to outside air temperature. And then from there, you can kind of have a rudimentary calculation for heating or cooling.
I should also mention, we actually have a version of this estimating project savings for HVAC coming up at the beginning of November. So it's not necessarily calculating kind of requirements, but it is calculating savings for projects. So it may offer some insights more specific to HVAC. And you can find out how to register on that on the Save on Energy events calendar. So check out the Save on Energy website and look for those events there if you're interested in that one. Great. So speaking of events, I think just to kind of wrap things up here, wanting to mention we're super excited about the Save on Energy awards that are coming up. Unfortunately, they are sold out, but we do hope that some of you we may see there. Super excited for that, to celebrate sort of successes in energy management, and also there's some trainings and workshops that are happening. So if you're not able to go this year, definitely keep an eye out for that next year around the same time. And then just to kind of wrap things up, we also have free expert support available through Save on Energy. And within that, there's an amazing energy manager learning platform and a discussion forum to get kind of advice and coaching and support on identifying and implementing industrial energy efficiency projects. So all about things we were talking about today and so much more. And for information on getting that support, you can go to training and support at the IESO.ca. And we've got about 2 minutes. I just really wanted to say, thank you so much to Todd and to Sean, and we have Fatema in the background here doing our production and helping us with all the technical stuff here. And really just to thank you to all of you for your time and attention, for your great questions. And yeah, we hope that we will see you next time. And have a wonderful rest of your Thursday, wherever you are in the world. Thank you. Thank you, Al. See you everyone. Seeing everyone popping off here. Have a great day. Right. Thanks, Tala. Thank you. Great. Okay, a few more folks left. So I think they're still saying goodbye. Great. We have Dawn, Peter, a few people. Fatema, I think we can probably clear out the room unless if anyone that's left has any important questions or anything to add, we can definitely, we have about a minute left, but otherwise we will see you next time. You don't gotta go home, but you can't stay here, so to speak. Excellent. Okay. Great. Folks are okay. That's
You
it.
see, someone has entered the lobby. Should I let them in just to quickly check if they had any questions? They
No,
had left the meeting previously and then came back into the lobby.
no, I think they
Okay.
can email if they have anything. Let's cut it off, I think. Yeah.
Sounds good. I'm just gonna stop recording.